But for you to understand, so please raise your hand and don't be afraid. Okay, you think a question is going to be stupid, forget it. I'll show you examples of the more stupid that I have done in this life. Okay, that's whatever you may ask. The discussions are very important. Why, Professor Silic? Discussions are very important. Different points of view are important.
But not allowed in the school.
Yes, they can have after 5 o'clock. So we can have discussions. Okay, the idea is not to create a labyrinth where one doesn't know where to go. There has to be some continuity. So we can have discussions after 5 o'clock. And then writing numbers in there, something, so that in the afternoon, okay, at 5 o'clock, you can say, regarding particular class number 3, okay, I didn't understand something. Of course, if possible, please interrupt me now. But if then you have questions, okay, this will be a reference point.
Yeah, it is.
Okay. Why Clifford algebra? For me, 30 years ago, if somebody tries to sell me Clifford algebra, okay, I would say, aha, that must be one of those algebras mathematicians have invented to make our life, the life of physicists, miserable. But this is not the case. I would have thought 30 years ago, you're going to tell me what I thought 30 years ago, you didn't know me. Okay, it is not so. Clifford algebra is Euclidean. You think, aha, I studied algebra and I only know about Euclidean spaces, 3 spaces. So, vector algebra must be Euclidean algebra. Nonsense. Why? For something to be called Euclidean algebra, it has to work in every Euclidean space, I mean, independent of dimension. But the Clifford algebra only exists about the vector algebra in dimension 3. Think of the vector product. In some dimension perpendicular to the plane of 2 vectors that you are going to vector multiply, there is a space 5-dimensional. Therefore, at least there is not a vector product in the sense of it has in 3 dimensions. You have a question? Still, there is an exception. In 7 dimensions, okay, you can still have a Clifford algebra. I mean, an assignment, a map, okay, any pair of 2 vectors, okay, of another vector. But we are not interested in that because also it will be specific to 7 dimensions, and who is interested in that? So, but the Euclidean, in the Euclidean 3-dimensional space, we have the vector product and the dot product. We are almost there. The problem with the vector product is that in reality it is the composition of 2, at least one of them more basic product, which is the exterior product, and another operation which is called obtaining the subscript. Okay, so what is going to happen is that, am I already in? The Clifford product, I use that symbol, eventually will ignore this symbol when it is convenient and simply put juxtaposition. Okay? So that sometimes we have, say, a B, and other times we want simply a B. When it's clear what we are talking about. So what is going to happen is, I'm going to write something like, if A and B are vectors elements of a Euclidean vector space. A Euclidean vector space is a vector space with a dot product. Otherwise, there is no need for a vector space, doesn't need to have a dot product. Plus, a dot B. Incidentally, in the literature, sometimes you will say definitions when they use that or say U and V, and other times you will see capital A, capital B, and whereas those refer to the same as those, vectors in the vector space, these are going to be more complicated objects. Some definitions will involve this, but it is simply because they are explaining what the algebra is. But for the most part, we shall assume that you know what an algebra is. And even if you don't know, you have practiced algebra since you were 5 years old, maybe I'm exaggerating. And therefore, algebra is natural to us. Okay, look at this very interesting thing. In some vector space, we have a pair of vectors, A and B, and look at the following, at this identity. Well, if you know what stereo product is, if you don't know the product, because I'm going to explain to you in a minute. This is going, okay, this is going to be identified with the stereo product. And we are going to identify this with the dot product. Those identifications are important because if I have here in terms of product, then this identification will be like that. Alright, that which is not stereo, it will be just that, it will be much more. Alright. So this is going to be the exterior product, and this is going to be the dot product. Alright, so now Professor here, please, I apologize if I now go never very, very low, but first there are some people working for mathematics here, or physics. There are some very, very junior students, and there are also 2 absent students, 2 ladies who will be here tomorrow. And the colleagues still younger will try to explain to them what I'm going to explain here now. So I am going to speak for a moment, for a few minutes at a very low level, but don't worry, I'll give you level 1. You probably won't handle later. Alright, level and style. This is why I have to apologize because I don't want any professor to feel offended. Stereo algebra. Well, briefly, stereo algebra is an associative algebra where we only need to have a B equal to minus BA. That is for the vectors of the vector space. The algebra is going to be built upon that vector space. Now I am in the vector space, and in the vector space, I am with A and B in the vector space. Okay, and A. Let me put this because otherwise it's going to be confusing for the moment. That's fine. Let me give you an example of a stereo algebra, how one operates with stereo algebra. So you are going to know the exterior product immediately. Let me write something. Okay, let me write something, anything you want. I am going to assume, okay, the English alphabet has 26 simple letters, and I'm going to assume that each letter represents a vector, and the 26 vectors are independent. They don't have to be orthogonal, nothing, just independent. So, this could be the 26 letters, I write that because it happens, this is the 5th letter in the alphabet, this is the 10th, this is the 15th, this is the 20th, this is the 25th. So you can be the letter R, or R is close to T, R is T. So the letter R would be the vector E, one of the 26 vectors, the one E and T. So this could be an element of the Clifford algebra in 26 dimensions if I replace those poles in here with plus sign times. And I think of juxtaposition as a stereo product, say this would be L, exterior E, exterior T, and if I convert that into this notation, J, K, L, this is the so this would be 12, exterior E, E5, and you understand the process. Okay, so this would be a general element of the parameter. It would be an element of general of the Clifford algebra of a built upon a vector space of dimension 26. Okay, let's compute. If those are stereo products.
Let's try, this is your approach, word Clifford. Right?
No, Clifford, yeah, that's an exterior.
No, the word Clifford, number, letter C, L, I, F, F, O, R.
I don't care about what Clifford said.
No, right, this is...
Clifford, no, well, actually,
right, as a vector. C is vector, L is vector, I is vector, F is vector, vector 3, okay, right.
L would be equal I. Now,
F.
I know why you want that, but I wasn't there. I'm in the lecture section. O could be E. Okay, anyway, we said the order.
No, but we must write F twice. Vector F, Clifford.
Here, E9. Okay, I didn't want to write so much. The idea is that if I have, okay, here it happens that all letters are different.
But Jose,
All letters.
this is 0 in Clifford algebra.
I know, but wait, please. I beg you. Okay, so the idea is something we don't know yet. Here, all the letters are different. Here are different. They are different. None of them is 0 because there is no repeating letter. But when there is a repeating letter, that term is 0. This is why it's very useful. This is why I want another continue because here we have repeated letter yet again. Whenever we have something repeated, because A equals minus B and A equals minus A equals 0. Therefore, any word in the alphabet in the English language, in your language, you can construct words which don't mean anything, okay, which has a repeated letter that will represent. Oh, the others are good. There are no many repeated letters. Okay, so I already, and why, whenever there is something repeated, the FF, this is E9, exterior E9, okay, so that is 0 because of that. If A equals minus BA, then the stereo product is 0. Objections?
No, that's right. Clifford equals 0.
We are not yet at Clifford. We are at exterior. All right, I'll get to Clifford right now because otherwise you're going to shoot me. All right, yeah, an interesting thing is that what would be the
That's like you're confused.
Okay. So now you know how to exterior multiply in a 2-dimensional space, but when we do those multiplications, we don't care whether we are in 26 dimension or in 189, provided all of them are linearly independent. Okay. A basis in the algebra will be constituted by, first of all the letters, then there will be the so-called two vectors. Now, I will not write BA, because BA and B are not independent, one is minus the other. Okay? So, I will have here plus, well, not plus, I'm not interested in adding them, I'm interested in enumerating them. Okay, B, C, let's take it out, B, Z, then I will start with C, D, and I will avoid of CA and CD because they are already as AB, etc. So that's the Clifford algebra. Now you know how to Clifford multiply. Okay? You want to say something you were talking, I could take any of your sentences, write them on the board, and then ask elements of the exterior algebra. Why is exterior algebra important? Oh, then I will start with ABC all the way to AD. CZ. And so on, I will take care of, I will write eventually BAC because, okay, this is related to that, they are not linearly independent because I will move this here and change sign. Why change sign? Because each time I move a position, I have to change sign. So I go from here to there by moving this one place. Okay, and this stops. If I had only 4 letters, say A, B, C, and D, this would stop at A, exterior B, exterior C, exterior D. Because if I repeat, in order to clarify, I only have 4 independent vectors. Okay, then at this point, adding one more will be either A or a B or a C or a D or a linear combination of them. That is it. So that's exterior algebra that you need to know to this point. Now I'm going to talk about Clifford algebra. Again, I use my I said, A, B for B. Maybe I'm starting to talk a little bit about what you are going to talk. Is it okay? All right, I'll go quickly with this. We said this. It is okay. Juxtaposition is going to be Clifford. Well, for the moment, I don't want to say this is general. Except that if this were a case of product, this would not mean much. Let's see what happens with IJK. We know that IJ here, okay? We don't say that it's K and talk, we just leave it like that. If you want to think of what IJ exterior J is, for the moment, think think of the plane, okay, built and made by two vectors. You don't have to think of the dimension of the space, because two vectors determine the two-dimensional space, and we don't need whether it belongs to a three-dimensional, it is embedded in the three-dimensional space or third-dimensional space, or whatever, it doesn't matter. The two vectors define the plane by themselves. Okay, it happens that ij will write like that. Okay, and I dot I is going to be 1, equal to b. And as for exterior, there is going to be ij, there is going to be jk, and ki. Now, what happens with I dot j? We know that the dot product, so that is 0, it's going to be ijk, it's ik, etc. So this reduces immensely. If I put here ij equals 1/2 atom me. No, I dot j plus I. If I have j equals, so if I have then this is 1, this is 0. And if they are different, okay, I and j, it is the other way around. If they are different, this is 0, and this is not. If they are the same, I, this is 0, and this is not. So to compute with orthonormal basis, is going to be very simple. Somebody will say, yes, orthonormal basis. Orthonormal basis are the canonical basis. Okay? And anything else is not exactly Euclidean, but a fine extension of Euclidean. Alright. Let us go back to our alphabet. Let us go back to our alphabet. Now we can have repeated letters. Okay? Now we are going to assume that the letters of our alphabet are going to be orthonormal vectors. Okay? Orthogonal and normal. If we assume that, then because of this, when I move to a round, because they are orthonormal, what is going to happen is that if I change position, I only have to reverse the sign. So, this is a bona fide, a good element of the algebra called simple multi-vector, because it is a product of vectors, it is not the sum of products that one can reduce. And if we want to order it, we would say, aha, this is E and D. We don't need to, but we have moved one position, so this one will be opposite of the other. And if we want to go back to notation that we have irritated mathematicians, we will put instead of E, we will put E. E5. This is Clifford, but since the bases are orthonormal, I can replace I can replace the Clifford product with this Clifford product. So it will be E5 equal to I. You know what I mean? Is there here what will happen in this one? Before writing with subscripts, I will do this next to this A, next to that A. So I move it one place, two places, three places. So minus A times A, I times I. Because the zero product is 0. Okay? So here I will have move this over there, I get a minus sign, n times a is 1, so this would be equal to LP HB with stereo signs. And now I can put them more than you wish by moving B to the front, changing spaces. No, LP, what you see here, the A is here, there some multiplication, stereo. I can move B to the front by moving in 3 places, so that will be B. And I will continue like this. And I think I don't need to insist, but move, because you're going to see a lot of this in Professor Gonzalez's talk. I just want to, when you read the specialized literature, you are going to encounter the term quotient algebra. I'll give you the concept of Clifford algebra by an example so that we don't have to invoke anything. Okay? We're going to encounter ideas, the concept of the quotient algebra. But it is the sophisticated, not necessarily for mathematicians' way, okay, of doing all this. But I'm going to compare now basis in tensor algebra with basis in stereo algebra with basis in Clifford algebra. You are raising your eyebrows. Clifford algebra is different from stereo algebra in one sense. It has to do with what is called grade. What does the grade mean? In tensor algebra, when you multiply a tensor of grade R with a tensor of grade S, you obtain or 0 or, well, no, only one is 0. A tensor of grade R plus S. In stereo algebra, it is either 0 or R plus S. In Clifford algebra, no. But fortunately, look at how they are related. The stereo products, so to speak, immerse as the anticipated part of the Clifford product, provided that at least one of the elements is a vector. This doesn't work for an object of this separation as a word doesn't make any. Is of no interest when I had an object of grade R greater different from 1 and S also greater than 1. Okay. In order to give you an idea, they call me tensor analysis, relatively sophisticated, but from the first half of the 20th century. Always be a basis in the tensor algebra. The big difference is tensor algebra goes from tensors of grade 0, scalars, to infinity. Okay? Whereas Clifford stereo algebra stops at a certain point, and so does Clifford algebra. What would be a basis in the tensor algebra? In tensor algebra, we would have first the scalars, say the numbers. Then we would have the levels of the alphabet. What would be grade 0, grade 1, grade 2, etc. Then we have tensors of grade 3. Oh, let me write 4. Let me write for just 3 dimensions, ABC. Okay, let me write all of them so that you see the difference. Here I will have in tensor algebra, I will have as a basis, for instance, with those A, B, and C, then BA, BB, BC, and so on. Now, correspondingly, what will happen in stereo algebra? This will exist. It will be 0. This setting. I will remove this because it is already there. Okay? It's solved. I will not enter into the dimension of the algebra and so schema,